Okay, we're bringing our next speaker, Nemanja Nikodijevic. He will tell us about the simplest Bitcoin hardware wallet. Welcome.
Спасибо. Я думал, если доклад будет на русском, но я думаю, что я еще не говорю русский так довольно хорошо, тогда я буду на английском. Дальше, если у вас будут какие-то вопросы на русском, можно спрашивать поздно. So, let's switch to English. So, about hardware wallets, of course, everyone is talking about blockchain, about bitcoins, about the new emerging disrupting technology. But and everyone is suggesting that it's gonna cure cancer, it's gonna be the cure for our problem. But well, yeah, all the sane people don't believe that, and those who were early adopters of this technology were, of course, initially using different software wallets to store their cryptocurrencies, but as this means of storing cryptocurrencies were not safe, many of them went to buy some of these hardware wallets that were more secure for storing cryptocurrencies. And let's see how these devices are built. Do we have the... Let's see. So you all know probably about Trezor and Ledger, two biggest ones. Okay, then I'm gonna. I guess yeah, I didn't set it to mirroring, so I'm gonna have to look at this screen. Anyway, let's see how these current hardware wallets are built. So Trezor and its ripoff KeepKey use just one simple solution with one microcontroller that talks to OLED and that talks via USB to the computer. And this microcontroller is just a normal off-the-shelf microcontroller that doesn't have any hardware acceleration it doesn't have any true random number generator, any hardware acceleration for the elliptic curve that one would need for Bitcoins, or for SHA-256. But since it's really simple, it can be completely, and it is completely open source, and that makes it really cool for people who are afraid that someone's going to hide something in closed source code, or that everything should be people who believe in open source, people from the open source community. Whereas Ledger, for example, it's built around the secure, it's built around also a non-secure MCU that talks via USB and also to the OLED. But it has also a secure coprocessor that is used for storing private keys, and it is meant to be as a more secure option for hardware wallets. We're going to see on the next slide why it wasn't. But it has hardware acceleration for that microcontroller is unfortunately under an NDA. So we cannot see the whole source code for Ledger, unfortunately, but at least we can see everything related to the communication to the PC and to the communication to the OLED and communication to this other secure microcontroller. How the signing is done, we cannot see that code, unfortunately. And there is a third solution that is out there that is really interesting. Instead of using secure microcontroller, using secure element. So last time I checked, this was, in fact, NDA was not required anymore for this secure element, but a couple of months ago, when I was started thinking about this topic, it was unfortunately still under NDA, so I left it like this, because when it was released, you couldn't find all the documentation for this secure element. But this secure element, from all the things that one would need for a secure hardware wallet, it doesn't have acceleration it doesn't have true random number generator. It only has acceleration for SHA-256 operation. It has, maybe the name might fool you, ECC, but it has it supports elliptic curve operations in hardware, but only for P256 elliptic curve. So we can forget about using it for the Bitcoin curve, the Koblitz curve, SEC P256K1. So, but it can be completely open sourced. On the other hand, the solution that I built this summer, like for over 3 months, as a sample project, as proof of concept, I wanted to see, is it the only way to solve this problem? So I thought having a USB running on the microcontroller where one would store, having a USB stack running on a microcontroller where one would store their cryptocurrencies and sign their cryptocurrencies. Like, if you find a bug in the firmware, which is like huge, usually drivers for USB device, then the complete security would be completely, the whole security ideas would fall apart. So I found an interesting microcontroller, which is when I looked into microcontrollers, the only one for which I didn't need an NDA and that had hardware acceleration for all the 3 basic ingredients for signing, for hardware signing Bitcoin transactions. And thus it can be fully open sourced. And on the board, I talk via serial, via UART to another microcontroller that is used for also programming it. So I'm using just off-the-shelf board for this microcontroller. And the communication microcontroller, which is with a concept like this, let's see how it measures, it compares regarding the threat model to other solutions that are already on the market. So in the normal scenario, people use hardware wallets because they don't trust software, and your computer can be hacked. We assume from the point of view that your computer is already hacked. That's why people are migrating to these solutions. And as you can see, if there is a bug in your USB stack, then one might be able to access and control the other microcontroller that is also controlling your OLED, and it can show you that you're signing this transaction, whereas it would actually sign some other transaction. And in fact, there were some buffer overflows and that were inside the USB stack for the Trezor code that were patched, and they have really nice blog where they talk about all of their vulnerabilities and how they fix them. Well, if we have a secure MCU in the setup like Ledger, well, I think this guy who broke their security model was just like 16 years old, the guy from the UK, which did a really, really amazing job. So, in fact, what they do, they have the setup like this, and the secure MCU is not just signing transactions, but it's also verifying the firmware running on the main MCU. So, I guess what you all think, like, what can probably go wrong? Well, if you put some wrong code on that microcontroller, you probably have some redundant code for USB communication in the bootloader and also in the firmware. Then what if you just when you have to send that code for verification to the secure microcontroller, you just resend something that is already there in the memory, and then you can put whatever code you want in the other redundant region. So that their security model is like if I would say that I have a twin brother that is going to continue this presentation, and if I just disappear and appear and say, okay, I'm his twin brother, and you are supposed to believe me. So that is basically how their security model worked. But apparently they fixed that. I didn't check the details, but it was already it already looked bad enough for me that there must have been some simple solution. So if someone gains control of the OLED, then we see this is the screen from Trezor, from one of the blog posts about their security. And this is, if we have a threat model like this, where we have a communication microcontroller that can be, even if that gets hacked, we completely shut down any possibility. We shrink the door for possible vulnerabilities on the other microcontroller. And what is really cool is that this communication microcontroller can also use all other, can be also used, for example, for Bluetooth, for Wi-Fi, for whatever. And usually these stacks are closed source, so you don't have many open software. So you usually have a library that does something like software device or something for Bluetooth Low Energy. And if you don't have control over that, would you really trust that microcontroller to also sign your transaction and store your keys? Well, not really. I wouldn't, at least. That's why this solution, even under these conditions, even under the assumption that whatever USB stack is running on it, and if this microcontroller gets exposed, this will maintain its security. So let's look at library dependencies of these projects. So Trezor and Ledger don't share, and even though they share the same hardware platform, they don't share any of the libraries. And this is just what these boxes mean. So the color-coded, the white boxes are open source parts of code, and the orange boxes are third-party libraries. So this is just the code that was taken from some other open source projects and just bundled with the rest of the source code. And you can see these dark boxes there. These are hidden parts of Ledger code that we are unfortunately unable to completely see because of the NDA for the secure microcontroller. And there comes the sidecar of Trezor, KeepKey, which basically reused all the basic libraries, and they just wrote their own firmware and bootloader part. And Coldcard that uses code from all of them. It combines all the software stacks. So let's see how they compare in the code size. So I cloned all of their open source projects in a directory, and then looked for the length of all the C and H files in their repositories, in their firmware and libraries. So Coldcard has 2.5 million, which is like just not everything is used, but since they, if you look at the previous slide, they use MicroPython. Because of that, it's just code size grows because there is support for MicroPython includes support for all the different microcontrollers. But then comes the Ledger. So only the open source part is like around 340,000 lines of code. And Trezor and KeepKey, they have, as expected, like around the same number of lines of code. And the solution that I came up with this summer, because I definitely, apart from my work, I didn't have enough time to write 122 lines of code. So I could only squeeze it into 4,000 lines of code. And that is because I was using basically hardware acceleration for everything. So I didn't have to use like bunch of libraries that other people wrote for many things. And out of these 4,000 lines of code, only around 2,000 is the actual meat. The rest is just a font for the OLED, for the display, and license headers, of course, majority, because I had to put them in every file. So you can find that on GitLab under this link, and let's see how this code is layered. So of course, the basic layer, all the core drivers, I try to keep them as simple as possible. So I didn't take any of the libraries that were already there for the microcontroller, but I had a look into them, and I just simplified. I used fixed numbers, so I couldn't choose a lot like different speeds. I didn't leave that into the code because this way the code can be much easier to audit, and it doesn't depend on many other libraries. And on the other hand, I even don't use the standard library. I compile it without even the standard library. So let's see how this maps to the hardware. So there is this UART side which talks 150 kilobaud link to the communication MCU, whatever that is. And then there is the other SPI bus that controls the OLED, which is fixed to 1 megahertz. And for that, I needed the SPI and GPIO modules. And on the other hand, these are the 3 modules that are used for hardware acceleration for signing Bitcoin transactions. And here it's color-coded. I don't know if you can easily see that this MMCAU is used for SHA-256 acceleration. This LTC is used for actually performing ECDSA. And I use two random number generator to generate a nonce. That easy. This is how it builds up. So I basically wrapped it around certain layers so that packets and packet receive, so that this, in case I want to port it at some time to another platform, I can just reuse this layer and just rewrite the whole bottom layer. So for sending these packets via UART, I have this simple structure, type length value, and of course CRC. And there is also CRC hardware acceleration in this microcontroller, which is really cool. Then for the OLED, I have just simple commands for like clearing the OLED and writing one row of one string in one row. And for crypto, it's a bit complex, so I had to add lots of these functionalities, because there is also when you do